All right, so just to give you a really quick summary of what we're talking about here, the motion that we've dealt with so far has all been this sort of thing, where you have a car or some object moving in a line. Maybe it moves in multiple directions, whatever, but it's translating. The whole object is moving from point A to point B. All right, and the whole object is moving as one. So the front wheel is moving the same distance as the back wheel, be it to the right or up or down or in a circle, whatever. Every point in the car is moving the same way. All right, so this is translational motion. We say that that object translates. Okay? But if you really think about it, we could have another type of motion, which I'll represent by this sort of wheel type thing, where there's still some motion, but not every part of this wheel moves the same distance. Right? So you can imagine that this point up here, if this thing were rotating, would move from this initial position to this final position. And we might say that, well, that's moved some distance s. Right? But if you look at this point down here, it's moved from here to here. We'll call that distance, I don't know, p. And clearly s and p are not the same length. So each part of this object does not move in the same way. And that's the difference between rotational, I keep doing that, rotational and translational motion. So you know about rotations, you know how things rotate, and that's what we're talking about here. We're going to start to talk about things that are rotating. All right, and all we mean really, all we're really talking about is objects that are spinning in place. All right, now the good news is that everything that we've done in the class so far is the laws that apply to rotational motion are basically the same. So what we're going to do now is we're sort of starting over. All right, instead of doing translational motion, we're going to look at rotational motion, but we're going to do the exact same things that we've done. We're going to talk about kinematics. We're going to talk about energy. We're going to talk about forces. We're just going to apply them to the rotational case. But all the physics is pretty much the same. All the laws, like there's Newton's second law, we're going to apply that to rotation. Work energy theorem still applies when rotations are involved. All the stuff we've learned so far. So there's not really anything new, which is why they jam all this stuff into 2 chapters. So chapter 10, we're going to focus on kinematics, and then we're going to do some energy. And then chapter 11, we'll come back and talk about how forces play a role. All right, so the first thing we're really going to be doing is kinematics. All right, so the laws of translational motion still apply. And that is good news indeed. But the thing we need to do, though, is really take a look at, there are differences. So we're going to take a look at those differences. So I'm just going to make a little table here. In translational world, we define things like speed, which is just distance over time. Well, now in rotational world, we still define things like speed, but we're going to call it angular speed. And instead of distance over time, it's going to be angular distance over time. All right, and so we're going to get to these definitions in just one second, the definitions of our basic kinematic variables that we're interested in. All right, but before we start that, I want to point out something very important. Whenever we're talking about angles, we typically fall back and use degrees as our angle. That's sort of common to do. We're familiar with angles. We know there's 360 degrees in a circle and things like that. But when we're talking about rotational quantities, generally we want to avoid using degrees. And the reason that we want to do that is because if we use degrees, we can't correlate these angles with any sort of linear quantity. And let me give you an example. So if you take a look at an object, and it makes a path like this. So it goes in a circle. Right? So it makes a circle. We know that the distance that this, what's the distance that this path, that this object has traveled? If I just say that the radius is some generic value r. All right. The distance that that thing has traveled is equal to the circumference of the circle, which is 2 pi r. Okay, so what I've done here, though, is I've related the circumference, which is a distance, which is something that we call an arc length, s, to the radius of my circle. All right, so if I take the arc length and I divide that by the radius, I get 2 pi in this case, in this example. But 2 pi, that's some angular distance. Okay, that's an angular distance. As long as that angular distance is measured in radians. Okay, so this is basically the definition of a radian. All right, a radian is equal to the number of radians that are subtended as an object rotates, is equal to the arc length, the length of that rotation divided by the radius of the circle. Okay, that's the definition of a radian. And for that reason, radians, we call these things radians, but what is the unit of a radian? Well, s is a length, so like meters. R is a length, so like meters. So a radian is really not a unit. It's just sort of a made-up unit. It doesn't have units. It's a meter divided by a meter. It's a length divided by a length. So we just call radians just to sort of give it something to, so we can associate it with an angle, but it's really a unitless quantity. So it's a sort of an imaginary unit. All right, and so this is really the reason that we use radians, because it allows us to relate an angular quantity to a linear quantity. And that's something we're going to be doing time and time again and when we're talking about rotational motion, going from rotational quantities to angular quantities and back again. So that's what we want to use radians. So that said, the important thing for you guys that are concerned about your grade at all times is that you note that when you're dealing with rotational stuff, when you're using that calculator thing, make sure you're in the correct units. Probably want to be in radians, though sometimes you might have to be careful and you might be in degrees. So just make sure you're using the right mode on your calculator depending on the calculation. Okay, so before we get into kinematics, let's take a look at what I'm really talking about here, though. So let's look at sort of as an example a space station. All right, and if you're a science fiction nerd, you might say if you're on a space station, one of the ways that you can create gravity on a space station is to make that space station rotate, and then what you get is sort of this centripetal force being balanced by the normal force of the floor, and that sort of seems like gravity. Okay, so if the space station is in this position at time equals 0 and it's rotating as I've indicated here, maybe a little bit later at time equals, 3 seconds, it might be in this orientation. Okay, so what we have then is it's rotated, from something like this position up to that position. If you're standing right here on the outside of the rim of the space station, you've traveled some distance s. You've traveled some distance s, and the question that we ask ourselves is, how is that related to this angle theta? Well, I just told you how that's related. But I can ask the question, I can ask that question, what is my change of position in a couple ways? So let me do that. So what is my change in position? I'm standing on the outside of the space station. I rotate from this point up to this point. and I ask the question, what is my change in position? Well, I can answer you in a few different ways. I could say that I rotated by, I don't know, it looks like 45 degrees. That would certainly be an accurate way to describe your change in position. I could also say that you rotate by 1/8 of a revolution. We're used to dealing with RPMs, revolution per minute, in this class, in our day-to-day life. So we could say that it rotates by some fraction of a revolution. Alternatively, I could say that we move by a distance. Moves by the distance s. And in this case, if I were to give you, if that's 45 degrees and I give you some radius, we could say that, well, maybe that radius is 39 meters. Just throwing a number out there. Okay? So the interesting thing about this is, okay, there's the space station. What happens if you, before building the space station, somebody probably made a model of it, right? They said, well, instead of, we need to model this space station before we build it, so that we can predict how it's gonna act once we build it at full scale. So in that case, let's say that the model was something like 1/100th of the size. And you have the same exact picture now, and you still want to describe the change in the position of some point on the rim. So again, you have a model now, and you've rotated. We're looking at the same picture. You rotate from this position to this position. So what is my change? What is the change in position? I'd still say it rotates by 45 degrees. 45 degrees. You'd still say that it rotates by 1/8 of a revolution. The only quantity that really gives us any information is the distance. That's the only thing that's different. And you sort of expect something should be different because, well, the size of the model is different. The distance traveled then, and if this model was 1/100th of the size, would be, instead of 39 meters, that point has traveled 39 centimeters. And that's really good because, well, that sort of gives you a way to relate the two systems. Some common factor that allows you to relate the two systems. And so what that distance is, of course, we know what that distance is. It's an arc length. And I told you just a second ago that arc length divided by the radius will tell you something about the angular distance that you subtended. So in this case, if we said it's in the full scale space station, the arc length was 39 meters. If I just give you a radius like 50 meters, what we come up with is 0.78. That's the factor that gets us from the arc length to the radius. If I do the same thing for the model, arc length divided by radius, now I have 39 centimeters. Well, the model is 1/100th the size, so we get 50 centimeters. Well, that looks pretty similar, so we get 0.78. And of course, if I do that, we know that the quantity that I've calculated here in each case are radians. That's the radians. So there's this link between a length and an angular distance. And that's nice because it's a way to relate different objects that might be of different sizes. So we'll be doing that throughout this chapter, the next couple of chapters. All right, so one thing you're going to have to do from time to time might be converting from some angle that's measured in degrees to radians. And if you want to do that, you just need to remember that if you have one revolution of something, that must be 360 degrees, because there's 360 degrees in a circle, and there's 2 pi radians. All right, so the conversion factor is 2 pi radians equals 360 degrees. And if you divide that out, you get 1 radian is equal to about 57 degrees. So that's how you convert, and you'll have to do that, like I said, from time to time. All right, so with that stuff under our belt, let's go ahead and talk about the quantities that we are going to deal with. So we're drawing parallels here between translational motion and rotational motion. So the quantities of interest for translational motion in kinematics were things like x, which was displacement. And of course, the units on displacement were meters. Similarly, in rotational motion, we have an angular displacement. And we give that guy the symbol theta. And we measure the angular displacement in radians. Translational motion, we had a velocity. And that was measured in meters per second. In rotational moment, we have an angular velocity. Which we give the symbol omega. That's a Greek letter omega. I know it looks like a W, I'm sorry. And we measure that guy in radians per second. Finally, in translational motion, we cared about acceleration. And we had units of meters per second squared. In rotational motion, we have an angular acceleration. We assign the Greek letter alpha to angular acceleration, and it has the units radians per second squared. All right, so these quantities are very, very similar. Instead of a linear displacement, we have an angular displacement. What is the angle between the 2 points of interest? How much did the object rotate? Instead of a velocity, a linear velocity, we have an angular velocity. How many revolutions per minute? That's the unit we're most familiar with, but we actually care about radians per second. All right, and then similarly for acceleration, instead of a linear acceleration, now we're talking about how many radians per second, how quickly are we accelerating in an angular sense. So to continue along our parallels, drawing our parallels, now we can look at kinematics. And I'm going to continue on my two charts here, my two lists. So if I were to write down my kinematic equations for, in the linear sense, in the translational sense, I would write down 4 equations that looked like this, that you guys all remember now, I'm sure. This one, xo plus 1/2 VO plus V times time, and then finally V squared equals V naught squared plus 2A delta x. All right, so those are our our translational kinematic equations. And as you might expect, the rotational equations look almost identical. We just swap out our characters. So instead of an x, we have a theta. Instead of v, we have omega. And instead of a, we have alpha. Going down the line, everything looks similar. Notice that time, still time. We don't talk about rotational time. All right, so the equations look very, very similar. And I don't spend any time derivating them because they're derived the same way as we did way back when. And I'm not really going to spend much time using them because you use them in much the same way. With the added benefit being that we don't really do two-dimensional rotations. So all the motion, all the kinematics that you're going to consider is all going to be in one dimension. It's all going to be one plane. We're not talking about some theta in one way and then a theta in the other way. because that's sort of hard to picture and doesn't really apply very often. So we're doing just 1D motion all over again, just with some new, with using Greek letters instead of Arabic letters. That's it. So the way that we're going to get practice is we're going to do a couple examples, and when I say we're, I'm really saying you are.
Can you back that break then?
To what?
At break, can you come back to almost the right point?
At break, can I come back?
When you're break,
Yep.
15 minutes, can you go back this fast so you write it all down in notes?
Sure. I could put it up there. I'll leave it up there as I write the example too. So let's do an example problem. Do it. Stupid spinning wheel of death. There it is. And so the first one we'll do is a helicopter. Bad color. So you have a helicopter and you're looking at the rotor. It turns out an angular velocity, and I'm sorry because I don't know how to do, so that's an omega. I know it looks like a W, it's an omega. I'll write it out just so we're not confused. Angular speed of 3.2, I should say 320 revolutions per minute. If the radius, I got to give you a radius of the rotor is 2 meters, I want to know what arc length is traced out by the rotor over the course of 300 seconds. All right, so you've got a helicopter rotor that's turning at some angular speed. All right, you're given the angular speed, omega, is equal to 320 revolutions per minute. You're given some time, equals to 300 seconds. And then the radius of this guy is 2 meters. So I want to know what is the arc length that's traced out in 300 seconds. Okay, now I want you guys to do this in like groups or subgroups. We'll do a couple of them like that. What's the first thing you have to do in this problem? Convert. All right, remember, we always want to work in the base units that we're supposed to be working in. So we have revolutions per minute here. You've got to convert that into radians per second. So that should be the first thing you tackle. I'm not going to tell you how to do that. I'll let you figure it out. All right, so go ahead and get into groups or subgroups. Work on this together, and then we'll talk about it. So in this problem, we could have an initial angular speed. We could have a final angular speed. We could have an acceleration. We could have a time. We could have an initial angular displacement, and we could have a final angular displacement. For some reason, it seems like no matter what you do with angular kinematics, we just always refer to, we always just assume that the initial angular displacement is 0. There might be a problem or two when that's not the case, but I mean, again, we're always talking about differences in quantities. So, it doesn't matter what theta 0 is. You could always call it 0 and just adjust theta final accordingly. So we'll just make this guy 0, and that's almost always how it's going to be. We have no acceleration, because I didn't tell you there's an acceleration. So the initial and the final speeds are both 320 revs per minute. And then my time is 300 seconds. And angular displacement is what we're after. So I know everything except for theta, so I know that I should be able to figure this out. Now the first thing we had to do is we have to convert. So I got to convert 320 revs per minute into radians per second. To do that, I got to get rid of my revolutions. So to do that, I know that there's 2 pi radians in every revolution. And then I get rid of my minutes by realizing that in 1 minute, there are 60 seconds. And if you do that calculation, you get 33.5 radians per second. Okay, so that should be your angular speed. After you do that, again, you have all the information you need. So you can just go ahead and pick your favorite equation. I'm going to go with theta final is equal to theta initial plus omega initial times time plus 1/2 alpha t squared. I have no acceleration. My initial angular position is 0. So I can solve for my final theta is equal to omega naught, which I just solved for, 33.5 rads per second times 300 seconds. That's equal to 1,050 radians. Okay? But you notice that I asked for what is the length traced out in 300 seconds. I didn't ask for what is the angle traced out. I want a length. So I need to calculate the arc length s, and I could do that by taking the radius and multiplying that by the angle. So the radius is 2 meters. I just calculated the angle in radians. Got to use radians. And so I get 20100 meters. All right, 20,100 meters.